Okay, so the microphone broke last time, and so what that means is that today I'm stuck with the middle board, which is why it's gonna have to cram things a little bit until we get a new microphone. But anyway, hopefully that'll go all right.
What do you mean they can't hear you?
So I have to put the microphone here, and then if I go too far, they can't hear me. If one of you holds it for me, I'll be happy to do that. Okay, so we were talking about lattices, you'll remember. And last time I talked about several properties that a lattice might or might not have. And these were the three that we talked about. Remember, first of all, a lattice is a poset where every two elements have a greatest lower bound and a least upper bound. A lattice is ranked if it has floors, and we said what this means. A lattice is semi-modular if the floors satisfy this semi-modular inequality. And a lattice is atomic if every element is a join of atoms. And we saw last time that lattices of flats have these three properties. Okay. So I'm going to define a new kind of lattice for you, which is a geometric lattice. It's a lattice which has these properties. It's ranked, it's semi-modular, it's atomic. Semi-modular, and atomic. I'll point out to you that I don't write ranked here because a semi-modular lattice has to be ranked. Semi-modular is a lattice that is ranked, and the rank function satisfies this inequality. So therefore, this is the definition of a geometric lattice, one which is semi-modular and atomic. Okay. So we know that lattices of flats have these three properties, so lattices of flats are geometric. And the main theorem, the most important theorem about the lattice point of view of matrices is that these are exactly the lattices of flats. So theorem, a lattice is geometric if and only if it comes from a matroid. If and only if it is the lattice of flats of a matroid. And this is the main theorem of the class today, and I'm going to spend the whole hour proving this theorem. And I think it'll help you follow the proof if I just draw once again the same lattice of flats that I had last time. So picture of the lattice of flats of the matroid that I keep using as my example. Okay. So here's the proof of that theorem. Now there's two directions, of course. And we already did one direction because we showed last time in class that lattices of flats are geometric. They have these three properties. So the first direction we did last time. So now we need the other direction, which is that if we start with a geometric lattice, we have to find the matroid that it comes from. So I'm going to start with a geometric lattice, and I'm going to build a matroid such that L is the lattice of flats. Okay? Now, the good thing about having so many different points of view for matroids is that now we can build matroids in many ways. So in order to build the matroid that I'm going to build, you can do it in several ways. You can do it using the bases, using the circuits, using flats, whatever. Now, since the defining properties of the geometric lattice seem to involve rank more than anything, I think the hardest of those three properties is this semi-modular property. And so because rank plays a very important role in the definition of geometric lattice, that is the definition I'm going to use for the matroid. I'm going to define a matroid by specifying its rank function. So I'm going to define a matroid on what is the set E? Well, I start with some lattice, and actually, so this is an example of a lattice of flats. But if I just tell you this is a geometric lattice, then what that means is that you don't know these labels, right? You cannot see them. So you have to make a matroid, but you don't even know what the ground state is. And it turns out that what we're going to use is the atoms are going to be the ground state. And this should already strike you as a little bit strange, maybe, because I started with a matroid whose ground state was 1, 2, 3, 4, 5, 6. Okay? And this other matroid that I'm going to build has a different ground state. The ground state is going to be these 4 atoms.
So you're losing loops.
I'm not going to actually try to. Am I trying to recover that same matroid?
So the thing is, I showed you how to start with a matroid and get a lattice of flats. But this might not be reversible, and it actually is not reversible. So what I'm going to do is go to some other matroid that has the same lattice of flats. So I'm not going to recover my original matroid, I'm just going to find some other one that also has that lattice of flats. The point being that, for example, this element 6 just gets lost when you go to the lattice. 6 is a loop. But if 6 wasn't there, you wouldn't notice in the lattice of flats. So you lose the loops, for example.
It looks like we missed the parallel attachment.
And exactly, the other thing that we're going to lose is that 4 and 5 always appear together in that lattice of flats. And so that's the other thing that's going to happen, is that you're just going to collapse parallel classes. So the matrix is going to be on the atoms of the lattice. Okay. And I'm going to specify the rank function. So the rank function is a function from the subsets of the atoms to the integers. So I'm going to define the rank of atoms E1 up to EK so So you start with the atoms, and what you're going to do is you're just going to take the join and see how high you end up in your lattice. So you're going to take the rank lattice of the element E1 join E2 join EK. Okay. I mean, if I force you to tell me what the rank of this is, then this is basically the only natural definition that you have. All right. Okay. So this on this ground set, I define this rank function, and I claim two things. First of all, that this actually is a matroid. So claims one, this ground set and this rank function does give a matroid. That's the first thing I need to show. And the second thing that I need to show is that this lattice of flats is actually L. So is it clear what I'm about to do? Okay. So step one is to show that this guy is a matroid. To show that this is a matroid, I basically have to show that it satisfies the rank axioms, right? And we're lucky that you guys did your homework, and we have an alternative statement of the rank axioms. And you guys showed that either you show the global rank axioms or you show the local rank axioms, and they're equivalent to each other. And it's going to be useful for us to show the local axioms in this case. So this is one application of your homework. This is actually why I assigned it. So we're going to show local rank axioms. And as you're used to by now, this is going to get progressively harder. So the first one, you're supposed to show that the rank of the empty set is 0. So what is the rank of? Actually, I'm going to ask you to not let me make this mistake that I made all over my notes, and I had to change all my notes. We're going to make this L curly, which I'm not used to doing, so I'm going to forget that. L is my geometric lattice, and this is the lattice rank function. So what is the rank of the empty set? The rank of the empty set is the rank in the lattice of the empty join. By definition, the rank of the empty set is the rank of the empty join, and just by convention, because it's the only thing that it could be, the empty join is the bottom element of the lattice. You can think about why that is, but the only reasonable definition is that an empty join is the rank of the bottom element, and so this is in the lattice, right? And we said that in ranked lattices, the bottom element has to have rank 0. So we're okay. The second rank axiom says that rank of A union A minus rank of A is 0 or 1. Okay? Okay. What is the rank of A? The rank of A as a set is the rank in the lattice of the join of the atoms in A. So let me give that a name. So let the join of the elements of A be X. And therefore the rank of A is just by definition the rank in the lattice of the join of the elements of A. What is the rank of A union A? Well, by definition, the rank of A union A is the rank in the lattice of the join of the atoms in A union A. In other words, it's this join A. Does that make sense to you guys? So let's just go back to the definition. So what is the rank? Remember, the E's are atoms, right? And so by definition, the rank of a bunch of atoms in my supposed matrix that I'm trying to build, by definition, what I have to do is take the join of those atoms in the lattice and see what rank that has. So if I want to figure out what the rank of A is, what I have to do is take the join of the elements in A to some element X of the lattice, and then figure out what rank that element X has in my lattice. Yeah.
And technically, when you write X join A, you're using the fact that joining is associated.
Right, so the rank of A union A is the rank in the lattice of joining all of these atoms. So I need to use that this is well defined, and therefore what I can do is join these guys first, and I get X, and then join A. So that's why I get this thing. Because more than anything, it's going to be a notational confusion, but the point is that the rank, the matroid rank that I'm trying to define, you just have to translate it into lattice rank. Okay. So now I want to show that this is equal to 0 or 1. Okay. How can I do this? Well, the only thing that I know about the rank function of this lattice is that it's semi-modular. And so probably what I have to do here is use the semi-modular inequality. And what does the semi-modular inequality say? Well, it says this. That the rank of, in the lattice of X plus the rank of A is bigger than the join plus the meet. In other words, this is what modularity says. Okay. You send this guy to this side, this guy to this side, then this is just the property of submodularity of L. This is because L is submodular. Okay. And now, what can you tell me about the right-hand side? Well, what is this number? The rank in the lattice of A. Remember, A is an atom. And so atoms have rank 1. So this is 1. What can you tell me about this guy? Well, it's smaller than A, right? It's A meets something. So it's below 1. It's either 0 or 1. Okay. So what I just showed is that this thing that I want is less than or equal to 1 minus 0 or 1. In other words, it's either 0 or it's 1. Okay. Questions about this? So there's my proof of R2 prime. And the last thing I have to show is axiom R3 prime, which says if the rank of A doesn't change when you add little a or when you add little b, then it doesn't change if you add both. Okay. And so again, my strategy is going to be to translate these things, which talk about the rank of my matrix that I'm trying to build, I'm going to translate it into the rank of the lattice. So the same thing. The rank of A, by definition, is the rank in the lattice of the join. I mean, just like I had here, the rank of A is equal to the rank in the lattice of X. The rank in the lattice of X. The rank of A union A is the rank in the lattice of taking X and joining A. And the rank of A union B is the rank in the lattice of X join B. So these are the hypotheses. But now you're going to look at this and you're going to see that, well, by definition of join, the join of X and A is bigger than X. X join anything is bigger than X. Okay? But then these two guys have the same rank, yet one of them is smaller than the other one. So the only way this could happen is if actually they're the same element in the lattice.
What do you mean when you say bigger?
Bigger in, so a very good question. Bigger in the lattice.
Higher up.
Higher up.
Right. That's all.
Now, actually, I don't want to say higher up because it doesn't mean it's on a higher floor. It really means that in the order relation of the lattice, X is less than or equal to X
So
join A.
some line connecting it.
So in the lattice, there's some sequence of lines that connects from X to X join A.
Right.
So I don't mean it's necessarily a cover relation, but it is.
There's a way to.
It is a way to wiggle up the lattice and say, you know, like you would say there 1, 6 is less than 1, 4, 5, 6 is less than 1, 2, 3, 4, 5, 6. So that's what I mean. You can wiggle up the lattice and go from X to X. Join A.
You can't really say that 1, 6 is less than 2, 3, 4, 5, 6.
Exactly. So in that picture, 1, 6 is not less than 2, 3, 4, 5, 6.
Because they're not. Because it's a
Because even though
partially ordered set.
even though it's higher, this is a partially ordered set, and if you don't see a path walking up, that means it's not smaller. In this case, 1, 6s and 2, 3, 4, 5, 6 are incomparable because there's no path going up from one to the other. But remember, by definition, X join A is an element that is an upper bound for X and for A. So just by definition, you have this inequality in the lattice. Okay. So if you have two things, and one of them is supposedly high, there's a path from X to X join A, and yet they have the same rank. Well, the only way that that can happen is if they're exactly the same element. Okay. And the same thing. X is smaller in the lattice than X meet B, and therefore there must be the same element because they have the same rank. And basically what I want to say now is, if this happens when I add A and this happens when I add B, then it also happens when I add both A and B. Why? Well, because therefore, if you take the if you take the join of X and A and B, what is this equal to? Well, again, I stated last time that this is associative, and so you can just do this in whatever order you want. So you can say, well, let me first do this, guys. So X join A is X. So I get X join B. And X join B is also X.
So does this mean that A and B were in your set capital A to start with?
Where A and B in my set.
Because if the greatest or whatever join of that doesn't change, it's just X. If A was some other atom that wasn't in X, it would have had to go up.
Yeah. Another way of saying this is that X is bigger than A.
Yeah.
But it
smaller than A, rather. No.
No, X is bigger
X
than
is bigger than A.
But I'm saying A had to be one of the things that you joined to get X
Yeah.
already.
Yeah. And that's basically what you're saying, that if A was one of the things that you used to join and get X, and B is also, then both A and B are.
Wait, is that true?
So A and B are in A?
In the original set A? Is that what you're saying?
Yes.
Yeah, so, I mean, remember what is the ground set of my matroid here? The ground set of my matroid is the atoms of the lattice. So A is a set of atoms, little a is an atom, and little b is an atom.
And what you meant, because what we did was if going back in our thinking over here, if M prime is sort of M throwing out the loops and the parallels, then we kind of only left the things that we need to build up. And so it is true that now if you think about the things that you could add in before to make it so that you didn't change rank, you could add in loops and you could add in parallels and you didn't change rank. Right, in some funny way.
So what is it that's worrying you?
Well, maybe I'm misunderstanding what someone is saying. So X is the join of everything in A, and you're saying that X is bigger than little a, and therefore someone was saying that meant that little a belongs to B.
Oh, I see what you're saying.
Yeah,
I see what you're saying. So let me first make a statement that one statement that I'm making is this, that this is equivalent to saying that X is bigger than A in the lattice. Okay? But Jeff's point is this, that I defined X to be some join of things some join of atoms. Now we just found another atom that is smaller than X. So what that means is that we might as well throw this atom into this union, and it's not going to change into this join. And if we were to add A into this join, it wouldn't change the result. But Jeff's point is that A did not have to be in this join to begin with. Because it could be that an element in the lattice can be written in different ways as join of atoms. Okay? And you can see that here. The top element of the lattice can be written in many ways as the join of atoms. It can be written as this join this, or this join this. If you pick any three atoms and join them, you're going to get the top element. So you don't have a unique decomposition into atoms. So this is what Jeff's point is saying, that okay, X is bigger than A, but that doesn't mean that A was in my decomposition of X that I started with. But, so what did I show? I showed that X join A, join B is equal to X, and therefore they have the same rank. X join A, join B is equal to the rank of X in the lattice. But by definition, the rank in the lattice of X is the rank of A. And by definition, the rank in the lattice of X join A, join B is the rank of A union A. Okay. And so that proves my third local rank axiom, and that proves that this actually is the rank function of a matroid. Any questions about this before I continue? It looks like some of you have questions.
So we actually proved something stronger here for our 3 prime. We didn't just say that the ranks are equal. We actually said that the joins themselves are equal, right?
Right. Right, which is more than we needed, but so what?
Wait, okay, so that means that A and B are in the closure of A. But A was supposed to be closed.
But hold on, because what closure? We don't have a matroid.
Yeah.
I mean, really, this is what this is saying, right? If we had a matroid, then this would say A is in the closure of big A, B is in the closure of big A, and the conclusion would be that A and B are in the closure of big A. If we had a matroid, but we don't. I mean, well, we do have a matroid because we just proved it, but we didn't have a matroid 5 minutes ago.
So now we're always looking back, now we have it, does that mean that means that A and B are in the closure of A?
Mhm.
But A is closed, so they have to be start with,
Why?
right?
Yeah.
Why was it closed?
It's on the lattice and flat. The flat.
Yeah, so I mean, in retrospect, the situation that we have is that now we show this is the rank function of a matroid. So that means we have closure, we have flats, we have everything. Okay? Now, this means little a is in the closure of big A, and little b is in the closure of big A. Now, what Jameson is saying is that big A is a flat. Is that true? Is big A a flat?
Yeah, has to be, right? There was something on the lattice. And we showed that was a lattice of flats.
What we haven't shown is that the lattice of flats of this matroid
We need to do that part.
is equal to L. So we will eventually conclude that A is a flat, but so far we don't know this because we don't know that the flats of this matrix are the elements of the lattice. Okay. But so what I've done so far is basically I proved the three axioms, and therefore I proved that I have a matrix. Done. Now, if I were to go in, I'll remind you of the picture. 1, 2, 3, 4, 5, 6. This was the matrix that we started with. From here we got this lattice of flats. And I just showed you a procedure to take a lattice of flats and get a matroid. The matrix that we got back looks like this. I lost my loop because my loop is not an atom. And I lost these two, one of these two guys. Here they were two separate elements, but they became only one atom. And that's why these two got merged and became this one atom. And so the point is that the matrix that I got from this construction is not the one that I started. But what I'm going to show is that if you do the lattice of flats of this guy, you are going to get this one. Okay, so this is a matroid. It's good. And now, what I want to show, so let's call this matroid M, which is what we like to call matroids. So the second thing that I want to show is that this is the right matroid. Maybe not the one that I started with, but it is a matroid whose lattice of flats is L. What do you guys think about that equality sign?
Well, I mean, maybe you want to try some more.
It's one of these things where, when I say equal, I mean they're the same picture.
Yeah.
But if you want to be really pedantic, then you want to say that these are really isomorphic because the elements of the poset are different, but what I want to show is that they're really the same poset. Okay. So this is what I want to show. And so if I want to show this, what I need to do is show you the isomorphism. I need to show you how to take an element of this guy and give me an element of this guy, and then show that that respects order. And actually, I'm going to find it more convenient to do it this way. And I'm going to write the map on this board so that I don't have to erase it. So I'm going to construct an isomorphism from L to LM. And I'll tell you what exactly it means to be an isomorphism of posets. But in any isomorphism, the first thing that you need is a map from an element of L to an element of LM. And this is what I'm going to show to you. So define a map from this lattice to the lattice of flats of the matroid that we have. What you're going to do is take an element of the lattice. Okay. And to that element you have to associate an element of the lattice of flats. What you're going to associate is this, the set of atoms A of the lattice such that Now I am, but in my proof I had to do it for any set.
When you say the set there, you mean the joint of this, or the? Because I want to.
No, because you see,
X is the joint of this.
L is a lattice.
No, I understand. So wait, so X
But-
is an element in one lattice,
So X is an element of
right?
L,
And I want an element in the other lattice to go with it.
right?
And so I want the.
LM.
This is the matroid lattice, so you need some set of.
So remember what is
Oh, I see what you're saying.
so I'll say M is a matroid on what is the ground set? It's
It's 1, 2, 3, 4, 5.
the set of atoms. So the ground set
So then, talk me over the very corner you're in. You had M went to L sub M.
maybe I should label these guys A, B, C, D. Okay. So for example, what is
Can I ask you my question about, it's a notational question that
Yeah.
going back and forth. Right where you're standing in the corner there, I started with the matroid M. I constructed its lattice, which was L sub M. From there, I constructed M prime, which is the matroid. So I think M prime is the matroid whose basis is the atoms of L sub M.
Oh.
You
I
what
see, so
I'm having a notational problem.
So the problem is that this M was not supposed to have anything to do with that M. So maybe you should just forget that this exists,
That's that M that we made.
because what we
So this is my, so okay, so wait, I got it, I'm back then. So that's M now. It's not
remember
M
that
prime.
the construction is I give you this lattice,
Right,
and
I got
there
you.
are no labels on it, and I just make up some labels.
I got you.
From here, I get a matroid. the elements of the matroid are A, B, C, and D.
Yep.
Okay. And now I have to define a map that for each element of the lattice gives me a flat here. So I'm saying, take an element of the lattice. Which one would you like?
I'll take that back.
Yeah.
This one.
That's a nice one. Yes.
I was saying if you would call it 1, 4, 5, 6 so that I could yell at you for calling it 1, 4, 5, 6. We don't know what this element is, but it's some element of the lattice. Okay. Where am I mapping it to?
Mapping it to A, D.
A, D.
And
These
the
are the
set.
atoms below. And I'm claiming that AD happens to be a flat. In this matrix. I haven't proved it.
Right.
It's not obvious.
I gotcha.
For example, if I had picked this guy, then I would look at the things underneath, B, C, D, and I would look here, and well, I'm lucky that B, C, D is a flat. This is not clear. But I'm claiming that it is a flat, and that actually this is the isomorphism that I want. So I need to check. The first thing I need to check is that phi is actually a bijection between these two guys. You need that for an isomorphism. Okay. This is the first thing you need in a posed isomorphism. And the second thing that you need in a posed isomorphism is that order is respected. So if one thing was smaller than another one here, then when you map over to the other lattice, the images should also be in that order. So x is smaller than y in my lattice, if and only if, when I map them over, they are phi of x is less than phi of y, but not in L. Because these things are in LM, so it's in L sub x.
So we're saying that the set,
Has rank less than.
yeah, so whatever we were saying there, that the set of x is smaller than, the set of atoms that are smaller than x is
So
smaller
remember-
than the set of atoms that.
Remember, what is the order in the lattice of flats of a matrix?
Oh,
It's containment. And so what this really means is that phi of x is contained in phi of y. Because this is the definition of the order in the lattice of flats. So this is a translation.
Where phi of x and phi of y are in LM.
Right.
So should our set, sorry, probably just messing up organization. Phi of x equals to atoms A of LM? No, just the atoms of L.
Yeah, because you see I started with L, and if I wanted to define phi of this element, I look at the atoms below and I say
Yeah.
phi of this element is A, comma, D.
Okay.
So phi of this guy is A and okay, so let's how do you show that this is a bijection between L and LM? Well, first of all, you need to show that it's well defined. In other words, that this set atoms such as blah blah blah, that should be in LM. Okay. So the first thing I need to show. So let me first prove. Okay, this is a bijection. So the first thing I need is that actually it is mapping where I say that it's mapping. Phi is well defined. In other words, the set of atoms A less than X is a flat of M. For all X in the lattice. the atoms that are under X better be an element of L sub M. It better be a flat of M, so I need to show that. So let's call it, well, I called it phi of X already. Suppose it's not a flat. If it's not a flat, that means that you can find, you know what, let's call it F, so the notation is a little simpler. So if F is not a flat, that means you can find some guy that you can add to it without increasing the rank. And in fact, let me make it clear that the rank that I'm talking about now is the rank of my matroid, which now I do know is a matroid rank. Okay. Now, what is the rank in the matroid of F? Well, by definition, the rank in the matroid of a set is taking the join of the set and looking at the rank in L. So if I want the rank in the matroid of F, what I want to do is take the join of all these atoms below X. But what is the join of all the atoms that are below X? It's X. So because the join of the atoms below X is X. Why is this? It's actually not obvious. But what you have to do is say, well, remember, this is a geometric lattice. If it's geometric, it's atomic. And if it's atomic, that means that I can write this X as a join of atoms. So I take my description of X as a join of atoms, and then if I add all the other atoms that are smaller than X, I can't go above X.
Yeah.
I'll let you think about this. This isn't immediately obvious, and it's only true if your lattice is atomic. But that means that the rank of in the matroid of F is the rank in the lattice of X. And the rank in the matroid of F union A by the same argument is the rank in the lattice of X meet this looks a little bit like what we had earlier. And now I want you to notice this, that the rank, so again, I'm going to use some modularity. I use some modularity, and then I use that the rank of X join A is the rank of X. So these two guys cancel out. And I get this, right? Which is not what I wanted to get, is it? expecting to get the opposite inequality. Oh no. This is easier. This is easier because the point again is that I have these two elements of the lattice. This one is bigger than this one. And they have the same rank. So if they have the same rank and one of them is bigger than the other one, then they have to be equal. Okay. Equal. And I claim that this implies that A is smaller than x. Why? Because A is smaller than the join of x and A, which is x. But if A is smaller than or equal to x, then it's in this list. Because this is the list of things that are smaller than x. So if A is smaller than x, that means that A is in F. But this is a contradiction because I should have said if my element F, if my set F was not a flat, then I could have found an element which is not in F, which doesn't increase the rank. So I would have assumed that A was not in F, and I got that A is in F. So there's my conclusion. This is a contradiction, and that shows that this actually is a flat, which is what I wanted to show. Okay. We're out of time, and I think what we're going to do is I'm going to ask you to read the rest of the proof in the notes and work through it, and if you want to see it, we'll finish it next time. Okay. But this is really the hardest thing. Now what we need to show is that this is actually a bijection and that it preserves order. So read through it, and if you want to do it next time, then let me know and we'll do it.